Hello and welcome. In this lesson, we introduced the second derivative test for checking the concavity of the functions. Before doing so, let's have a summary of what we have covered so far with respect to the increasing-decreasing behavior of a function using the first derivative. Take the function y is equal to f of x. If prime of x, or the first derivative of x, is positive, the function is increasing on a and b for all x in a and b, of course, when the first derivative is defined. And the function is decreasing on a, b if prime is less than 0. Based on Fermat's theorem, if the function has a local maximum mean at an interior point n, and the derivative is defined there, then the first derivative at that point is 0. Take this example of y is equal to x squared. As you see, for x less than 0, this function is decreasing. At x equals to 0, the function has a local minimum. Therefore, there, the derivative is 0 because it's a smooth turning point. And then for x bigger than 0, the function is increasing. In other words, for x less than 0, if prime is negative, for x equals to 0, if prime is 0, for x bigger than 0, if prime is positive. On the other hand, if you take the function y is equal to minus x squared plus 4, you see that for x less than 0, the function is increasing. At x equals to 0, it has a turning point which has a local maximum where the derivative is 0 because it's a smooth turning point. And for x bigger than 0, the function is decreasing. In other words, here for x negative, if prime is positive because the function is increasing, for x equals to 0 if prime is 0 because that's a turning point, in fact that's a local maximum, and then for x bigger than 0, if prime is negative. Take again the function y is equal to f of x, and suppose that we have a local maximum and minimum at an interior point n. If prime changes from positive to negative at point n, that means from increasing behavior to decreasing behavior, then the function has a local maximum at point n. Likewise, if prime changes from negative to positive at point n, from decreasing behavior to increasing behavior, then the function has a local minimum at point n. If you look at this, the function is decreasing up to this point here. Then at this point, it has a local minimum, and then it starts increasing. You see that the function's behavior changes from decreasing to increasing. In between, it attains a local minimum. If you look at this point here, the function is first increasing, then decreasing. That means the function changes from an increasing behavior to decreasing behavior. In between, it has a turning point, which is a local maximum. Likewise, if you look at this point here, the function is first decreasing, then at this point, there is a turning point. The function is increasing then later on. Therefore, in between, it has a local minimum. You see that the first derivative negative, then positive. In between, there is a local minimum. The first derivative positive, then negative. In between, this is a local maximum. Likewise, here, this is a local minimum. The concavity of the function is defined using the second derivative. But first of all, we need to define the concavity of the function. Suppose we have this function y is equal to f of x, and the first and second derivatives of this function is defined. The graph of function f is concave up on an open interval I if prime is increasing at that interval. Remember that if prime itself is a function, it can be increasing and decreasing. The graph is concave down on this open interval if prime is decreasing at interval I. Since the second derivative of the function is defined, we can use the second derivative of the function in order to check the concavity of the function. Remember that we have f prime increasing. That means if double prime is positive, then the function is concave up. If double prime is negative, then the function is concave down. Take this example of y is equal to x squared. You see that the second derivative of this function is actually 2, and that's positive. Therefore, this function is concave up. While this function minus x squared plus 4, the second derivative is minus 2. Therefore, this function is concave down. As another example, take the function y is equal to x to the power of 3, this function here. And then take the first derivative. The first derivative is 3x squared. Then take the third derivative, which is 6x. That's this function here. The second derivative is negative for x less than 0 and positive for x bigger than 0. Therefore, the function y is equal to x to the power 3 is concave up for x bigger than 0. That's this part here. And concave down for x less than 0. The second derivative can also be used to test whether a function has a local maximum or a local minimum. Take the function y is equal to f of x and suppose it has a local maximum mean at an interior point n where the first and second derivative is also defined. Then using Fermat's theorem, we know that at this point f prime of n is equal to 0. Now in order to specify whether we have a local maximum or a local minimum, we take the second derivative. If the second derivative was positive, we have a local minimum, and if the second derivative was negative, we have a local maximum. Take the example of y is equal to x squared. If prime of x is 2x, we let this to be 0 in order to find the local max or mean. From here x is 0, and if we want to find y, we insert x here. 0 squared is 0, therefore y is 0, therefore 0, 0 is either local max or local minimum. In order to specify whether this is a local max or mean, we take the second derivative, which is 2. Now 2 is positive, therefore the function has a local minimum at point 0 and 0. Take the example of minus x squared. The first derivative is minus 2x, let it to be 0, find x, x is 0, find y, y is 0, then we have 0 and 0 is either a local max or mean, and take the second derivative. The second derivative is negative, therefore we have a local maximum. As the next example, take the function y is equal to f of x, x power 4 minus x squared minus 2, which is this function here. This function from the graph, we can see that this function has a local minimum here, a local maximum there, and a local minimum there. To find the location of these critical points, we take the first derivative for x power 3 minus 2x, let it to be 0 and solve it for x. We get three solutions. 0, 0.71, that's here, minus 0.71, that's there. Find the corresponding y values, that's p1 is 0 minus 2, 0.71 minus 2.25, minus 0.71 minus 2.25. These are the three critical points. Now, in order to specify which one is a local maximum and which one is a local minimum, we take the second derivative. If double prime of x is 12x squared minus 2, then if double prime of 0 is actually minus 2, therefore this is a local maximum. In other words, we evaluate this f double prime at 0 at this point 0.71 and at this point 0 minus 0.71. If the result was, or the resulting y value was negative, which is the case for 0, then we have a local maximum, which is this one here. If double prime of 0.71 is 5 point something, which is positive, therefore we have a local minimum there. And likewise, if double prime of minus 0.71 is 5 point something, which is again positive, therefore there we have a local minimum too.